slide at the e-learns, you can actually check at your e-learn. I have also uploaded the previous lecture on mechanical assembly. All right. Basically, this heat treatment you have actually gone through during second year EBB 225. I'm not sure who teach this part, either Dr. Nurul or Dr. Badri. I think your batch is Dr. Badri. Okay, I will not go through all the details on each of the heat treatment because the common heat treatment for steel is annealing, normalizing, hardening by quenching, and you also have tempering. And beside that 4 heat treatment, you also have spheroidizing. Spheroidizing is actually almost similar to annealing, but the soaking time they actually prolong the soaking time. Normally they will not heat above A1, which is at the austenite region for full annealing concept, but they will heat at below A1. So what they actually expected a very dark cloud. So what happened here, the lamellar structure of cementite will change to become spheroid structure. So that's how they call this process as spheroidizing. So this is actually tend to make the material become ductile for easy machining. So but don't confuse with tempering. So tempering also will make your martensite become spheroid structure. But this is different. Spheroidizing and tempering is are different thing. Okay. So this is another heat treatment which is not covered. I think it's not covered during 225. Also, actually not covered because it's seldomly used. Yeah, you only cover the common use, which is annealing, normalizing, hardening by quenching, and tempering. You also have tempering, which is to form binite. So this one also you can actually read. And we also have martempering. Martempering is a heat treatment that actually form martensite, but this is less distortion because you allow the material to be quenched above the starting of martensite. Then only after that you let the material to cool, follow the martensite's formation. So this actually helps to reduce some distortion, because if you use hardening by quenching, you directly quench the material from the higher temperature towards the lower temperature. So this can actually cause some cracking or stress induced in the material or distortion. So basically, this is definition. I think you guys can go and read. I won't actually go one by one because we have actually also covered this one in a lab. So this is some of the actually objective of heat treatment to soften a metal for forming. So this is actually prior to shaping, means that you're going to make this specimen become ductile. So which are the process that actually make the specimen become ductile? Proses apa? Sebelum you masuk forming, what you have to do to ensure that the materials has some certain ductility, so that when during the process of deformation, either metal forming ataupun sheet metal process, this actually will not be cracked. Apa proses dia? What's the heat treatment? Saya minum dulu, saya tak sarapan lagi. Okay, good. Annealing. So annealing has two concepts. One is actually to release the to make the material become ductile for the process of deformation. Annealing also can be done after the process of deformation. So this one we call as stress relief anneal. So what are the difference between process anneal or stress relief anneal? So one is done before the process of formation. The other one is done after the process of deformation. So remember that if you can recall back what you have learned before, we have 3 stages of annealing. One is actually at lower temperature we call as recovery. So the second stage we call as recrystallization, and the third stage we call as grain growth. So when you want to do a process of process anneal, you have to heat until grain grows. So that make the material become ductile. But after the process of deformation, you just want to release some of the stress that was induced during the process of deformation. You just do at the recovery stage. So meaning that you doesn't have to heat the material up to austenite region. But for the first process, for the process anneal, you have to heat above the austenite at the austenite region. If you can recall back, we name as A3 or ACM. It depends on the compositions of carbon. So you have to heat above that line. But for stress relief, you heat below the A1. Just enough to ensure that the stress, some stress that was induced, release out from the part. So that during the service, there's not much stress is inside the material that can cause stress cracking corrosion, and also a potential site for crack to initiate. So the second one is the third one. This is what we mean by to relieve strain hardening. So this is what we call as process anneal. So the last one is to strengthen and harden material. So what is the process? Apa proses ni? Untuk strengthen dan harden. Apa dia punya heat treatment dia? Dah lupa dah. Heat treatment dia apa? Benching lagi. Normalizing also can be done. Tempering. Okay, tempering you can actually also done after the process of benching. So you can also do annealing, but annealing you have to do at the recrystallization temperature, meaning that you have to ensure that the temperature that you select for annealing at TR temperature. What is TR temperature? If let's say you have a metal, so what are the formula for you to determine the TR? Apa formula dia? You belajar 225, you belajar 344. Apa formula dia? TR equal to berapa TM? TR equal to how many TM? It's a general 0.4 TM. Okay, good, Zenyu. Okay. All right, cool. So some books name as 0.3 to 0.4. It depends on the type of material. If let's say pure metal, so definitely dia perlukan high temperature as compared to low alloying. Okay. So this is basically I won't go details on this. All right. So this is some of the reason for annealing. This is the process of annealing and soaking. And it's the same thing here. So that's why I remember I told you just now. So this is what we call as process anneal. Right. So some people call also anneal if the deformation is not process. If let's say the first part you do then after the first part, then you go to second part, they call as process anneal. It depends on the production. So some call anneal, some call process anneal. But the second process we call as stress relief anneal, as what I mentioned to you. After deformation process, then only we want to release some stress, they call as stress relief anneal. So this is some of the all the information that you have to find from the Martensite. So kalau you all tak ingat lagi, mana gambar yang saya tunjuk? This is actually the phase diagram. If you still can't remember, so I have to recall back here. This is ACM. This is A3. This is ACM. Ini A3 yang macam V shape ni. Ini adalah ACM. So whatever you want to do the heat treatment, you have to heat at this region. It depends lah. Kalau full annealing, kalau nak sampai grain growth, kena heat dekat austenite. Same goes to normalizing. Tapi kalau nak buat stress relief sahaja ataupun dekat recrystallization temperature, you akan heat below A1. This area, okay? Okay, so this is also another graph is time temperature transformation. So I will not go details. So this is actually for formations of martensite. Just now I mentioned for mark tempering. So they will actually quench until this temperature. So they'll normally use salt, right? Because they can control the salt's temperature. So what they do, they will quench in the salt. So ensuring that the salt temperature is above the martensite starting temperature. So then only they will cool it slowly following the path of the martensite's formation. So in this mark tempering, you can actually reduce the distortion. So this is actually this is some of the step. Okay, ni tengok gambar ni. So kalau you tak ingat lagi martensite, you remember this picture. So you can see that this martensite is very stunning, right? Dia macam cheeky. Tapi dia tak stable. It's not stable as compared to perlite. So dia nampak macam menarik, stunning, but it's not actually stable. They are metastable. So that's why martensite normally they have to temper, not for perlite. So austenite will form martensite at certain cooling rate, and in these cases martensite is really hard but it's not stable. So you can actually flashback this picture. Kalau kita ingat sangat apa itu martensite kan susah bila sampai finally pun tak ingat lagi martensite tu apa, perlite tu apa, austenite tu apa. Perlite ferrite tak ada dalam gambar ni. Okay. Alright, so this is metal quenching medium. So I won't actually go details. So this is some of the quenching media. It depends on the rate of the quenching rate that you wanted to be. Okay. So tempering saya tak akan pergi. Okay, hardenability is actually a process that is not a measurement of hardness. So kamu perlu ingat bahawa hardenability ni bukan measurement of hardness. Bukan maksudnya lebih harden, lebih panggil macam mana? Hardenability test bukan measurement untuk hardness. So dia it actually measuring the depth of the sample. So means that how much actually the case depth that the material will be able to achieve a certain hardness. So if you have a good hardenability, so you have more depth. You have more depth of hardness that achieve a higher hardness as compared to material with low hardenability. Boleh faham tak? Hardenability ni normally kita nak achieve case depth, means that you are turning the external structure to become more hard. As an example that you are actually forming a martensite structure, right, at the outer structure, then only you go for tempered. So when you measure the hardness from the surface towards the inner, so you will see that the hardness will be higher, and after a certain depth, the hardness will be dropped, right? Saya ada buat ini gambar. Like this. So when you measure, so this is actually distant from the quench, right? So you can see here the hardness is actually higher at this region. So it will be dropped after it go to the inner side. So if you have case of depth is bigger, it's actually larger as compared to another material. So means that this material is more hardenability compared to the other material. So this precipitation hardening is for material with for non-ferrous. So the one that we use for annealing, normalizing, hardening by quenching and tempering is for ferrous alloy. But for non-ferrous, we go for precipitation hardening. So we can use either T6 for precipitation hardening, or we can actually use T5, use T4. So that's some of the heat treatment method for non-ferrous. But the common one is the precipitation hardening, which is T6. So you have to heat at the solution, make it as a solution treatment. So heat at one single phase. Then after that, you are followed by the process of quenching. So after that, you heat back to forming the precipitation we call as aging process. So I want to actually go detail here because you have actually learned this. It's a similar to hardening by quenching. So you heat to phases that only single phase. So then all the beta will be dissolved and forming only single phase. Then after that you quench it. Then after quenching you heat it back. When you heat it back, so you must ensure that this is what we call as aging. So you must ensure that the aging temperature that you select is not actually enlarge you punya precipitate. So you not have to acid over aging. So only certain temperature that allow for the precipitation to take place, and also the time. The time, soaking time also play important role here. So not as, because when the precipitation is actually precipitate, it must precipitate in the lattice. Kita tak nak dia precipitate sebagai satu fasa lain. Maksudnya bila kita biarkan dia lama, so dia akan become decoherent daripada matrix. So bila jadi tak coherent, so dia punya strength tadi tak berapa kuat as compared dia coherent dalam matrix. Maksudnya ini adalah aluminium. So the precipitate embedded in the matrix, it become another structure that semi-coherent ataupun coherent dengan matrix. Semi-coherent ataupun coherent. Kalau dia tak jadi non-coherent, maksudnya dia dah become its own structure. Dia keluar daripada matrix tadi. It's not actually, the strength is not actually high. So we don't want this. This is what we call as overaging. So this is all you have learned. So I think you have repeat many time in this ada lab dan ada juga dalam kelas. So sampai saya kena repeat juga sebab dia adalah dalam syllabus 441. So this is the process. Okay, so I'm going to touch on this surface hardening. So surface hardening normally we do to increase the strength, the outer strength of your specimen. So what we actually do, we have carburizing, nitriding, carbonitriding, chromizing, and so on. So what are actually the reason to harden the sample? So this is actually to definitely to increase the wear resistance, increase the surface strength, compressive stress. So they produce tough core for resistant to impact. Maksudnya dia nak make sure that dalam core dia toughness, high toughness, ada ferrite and for example kalau kita guna non-ferrous, ferrite and pearlite, but the outer surface will have a tempered martensite, so that you still have a tough core but you can resist the impact because the outer surface is hard. So this is what we want. We don't want that all the structure become tempered martensite or tempered martensite. Kita nak satu jadi at least jadi ductile and become a core, but the outside become hardened. So this is what we call as surface hardened only. Kita nak surface saja yang keras. For certain purpose kalau untuk application untuk wear, definitely diperlukan harden saja yang hard. We don't want all the sample to be hard. Because some of the application it requires some movement. Kalau both are all become hard, so sample tu tadi tak boleh retain so long because you need some of movement. You kena ada juga toughness ataupun ductility. Okay, so this is some of the compositions that used for machining part that require a hard surface. For example, gear. So you need a tough core but hard outside. So shaft and cams. We also have mana dia lagi? Sini. Sama juga. Gear, semua je gear. Okay, automobile part, steering work, overhead, and valve mechanism. Valve mechanism. So all these require hard surface, but they also need a core that which is ductile. So this is actually why we do a surface harden. So this is some of the case hardening process that normally people actually use: carburizing, nitriding, cyaniding, chromizing, boronizing, and carbonitriding. And we also can use heat treatment. But when you use heat treatment, bear in mind that, for example, like induction hardening, flame hardening. So you require a material that's already have a certain amount of carbon. If let's say you use for steel, right? So because you unable to use low carbon steel to form the martensite, you have to have at least medium carbon, right? So when you use this type of heat treatment to get the outer surface harden the outer surface, so the material that you have to use, you must use medium carbon and above. So if you have low carbon, so definitely you have to go for carburizing. Boleh faham ke tak? Ataupun sudah beletih? Boleh faham tak ni? Kenapa kalau kita nak ada kalau kita nak guna low carbon, kita tak boleh guna induction heating ataupun flame hardening. Because sebab kalau kita guna this method, we don't have enough carbon to form martensite. So it's no use. Kalau you buat induction hardening untuk heat treatment for you to get the surface hardened, so you won't get. Sebab carbon yang you ada tak cukup. So that's why you kena buat carburizing dulu. Then only baru you akan follow dengan quenching and tempering. But if you have sample that memang ada medium carbon, then you can directly use this method. Faham ke tak? Faham ke tak? Okay, tak apa. Alright. Afifi seorang yang faham. Yang lain? Okay, so this is actually concept of case hardening. So that's why dia kata normally kita akan add carbon or nitrogen. So you can see here that commonly used to low carbon. So when you have low carbon, so you're unable to proceed with the heat treatment. So you have to embed the carbon first. Masukkan carbon dulu sebab dia kurang carbon. So bagi dia makan carbon banyak. So bila bagi dia carbon, then only you can turn the outer surface to either medium ataupun high carbon content. Then only you follow by process of quenching. So it depends on here. Kalau kita guna nitrogen, kalau kita diffuse nitrogen, so you don't have to go for quenching because nitrogen kita kena make sure that dalam steel kita tadi ada former yang boleh form compound dengan nitrogen. So you kena ada macam aluminium yang boleh form compound dengan nitrogen that can actually harden the surface. So we go back to what we have learned before. So certain material akan jadi solid solution dan certain akan form compound. So this is some of the term selective heating, case depth. So this is the term that we will actually cover later. So I'll skip this slide. Okay. So this is some of example steel used with low carbon. You can see here this is the ASTM. The name dia punya numbering dia 1018. So this is actually 0.18% of carbon, right? So this is 0.2% of carbon. This is 0.22% of carbon. So this all considered as low carbon. So we can actually use case hardening because we can control depth. So kita boleh dapat depth yang kita nak. How much case depth that we want. If let's say too small, so maybe it cannot prolong the life of that part, right? So you have to have certain case depth to ensure that punya lifespan of the part is actually enough. Maksudnya service life dia cukup. Okay, work well with for a complicated part. So kita boleh guna semua part. You don't have to worry on the complex part. So definitely dia murah dan dia boleh mudah untuk kita buat kepada mass production. So dia punya material starting also will be very cheap because you use low carbon. So then you will have, as mentioned before, you have a tougher material inside, okay? Tough structure than medium or high carbon. Because you have a tougher structure inside because definitely low carbon has less amount of carbon. So then they will have very ductile as compared to medium carbon and also high carbon. So you can have the outer surface is very hard but the inner surface become very ductile. So we go one by one. We will actually talk about first which carburizing. So you are actually diffuse carbon in the samples. You can do either by solid, kalau kita buh charcoal, kita pack, ataupun liquid carburizing. We also have gases of plasma source. So this one we have to hit above around 900 so that we can actually combine two process together, while one diffusions of carbon and as well as the heating the sample up to austenite region. Kan? So bila the carbon diffuse, so you have to hit a certain amount of time to ensure that when all the carbon are diffused and the temperature of outside are bringing up to the temperature of austenite region. So this is some of the example of dia punya solid, kita panggil pack carburizing, kita letak charcoal, kita pack packing the sample with the charcoal. So normally kalau industri dia guna gas carburizing. So dia guna propane or other cases that dalam enclosed furnace, maksudnya dalam furnace yang tertutup, ensures that these gases are actually will be dia tak ada any casing tu tak ada terkeluar, maksudnya dia dalam keadaan tertutup. Okay. Liquid carbonizing kita letak dalam molten baths dan containing sodium cyanide, NaCN and barium chloride. So this is some of the source of the carburizing. So you have to quench because when the carbon diffuse in the sample, so for example this is the sample, so carbon diffuse to samples, it won't actually diffuse until the inner surface, right? They can diffuse only at the surface sahaja. So when you have enough time when the carbon have enough diffusion inside this area, so you have area of maybe medium carbon or high carbon surrounding this area. So after that you will be quenching. Normally kalau industri dia guna oil quench. So yang quenching, so the furnace tadi akan dia punya sistem tadi akan jadi one line. So after carburizing, then quenching, dia masuk tempering. Okay, so hardness is about 100 HC 60. Selalunya depends lah. Kalau 60 lebih tu kiranya kita dah dapat martensite. Okay, ada 67, so it's around that. So this is what this is some of the mechanism of carburizing. You can see here that this is actually the punya concept. This is part to be carburized. So you akan induce the carbon. So this is gases carbon monoxide and normally dia guna carbon monoxide dengan hydrogen. You can see here that so this is the explication. When the carbon diffuse, dia akan jadi solid solution ataupun dia akan jadi dia akan form Fe3C, kan? Dia akan form carbide. Dan dipanggil precipitation hardening ni lah sebab dia akan form satu lagi compound which is carbide Fe3C, ataupun dia jadi solid solution dalam steel tadi. So ada dua konsep, satu primary solid solution, satu lagi secondary solid solution. Right, so this is actually the atom carbon. So the atom carbon tadi akan diffuse dekat lattice of dekat interstitial site sebab dia kecil kan. Kalau dia kecil dia akan masuk dekat interstitial, dia duduk kat sini. So dia tak boleh terlalu dia tak boleh sampai ke tengah lah sebab it depends on dia punya Fick's punya law. Ingat tak Fick's law? Kena recall balik Fick's law lah macam sebab dia bergantung kepada temperature and time. So normally kita nak harden only certain area sahaja. So we can actually calculate that and see how much actually the time and the temperature needed. So bila carbon tu dah masuk, so bila ingat tak bila dia masuk dekat interstitial tadi dia akan jadi solid solution strengthening. Dia akan jadi interstitial solid solution. Dan bila dia have enough carbon yang masuk, dia akan form another compound kita panggil cementite, Fe3C. So this is example of gas. Kita boleh guna sama ada carbon monoxide, carbon dioxide, hydrogen, methane, water and carrier gas of nitrogen. So all this actually, this is some example. Kalau you guna methane plus carbon dioxide, so you akan dapat carbon monoxide dengan hydrogen. So this one is with these gases, so carbon akan diffuse and they akan form molecule of water. So this is some of the example you can see here. So this one they are using actually methane tadi, kita akan produce carbon monoxide and hydrogen. So then the carbon will be diffused in the sample and leaving water. So this is our packed carburizing. We are using the solid. You can see here that you have different temperature. So if you have a lower temperature which is 900, you akan guna masa yang lama, 40 hours. If you use a higher temperature, so you can get depth case tadi 2.5, maksudnya depth case tadi hardness you tadi besar, dia punya jarak dia lagi besar dengan masa yang lagi singkat dalam 15 hours, right? So if you want the same depth case with 900, you have to heat at 40 hours. So it depends on the temperature that you select. So this is a difference between solid, gases and liquid. So you can see here that gases took less time as compared to solid to reach the same depth of case. Depth case dia sama tapi gas lagi cepat lah berbanding dengan solid and liquid. So dekat sini dia guna carbon steel 0.5%. So you can see that different source can have different time. Dia punya, kalau solid dia lambat sikit lah. It take more time for the carbon to diffuse. So this is example of sample that have been carburized. So you akan dapat ini, akan dapat hypoelectric zone, maksudnya banyak carbon lagi banyak kat sini. So when the go to inner, you can actually get electric structure, and after that hypoelectric, because carbon are keeping lesser and lesser, and after that you akan dapat carbon sama dengan you punya sample. Let's say you start with 0.2% and the carbon still hypo lah, sebab 0.2 fall under hypo. Boleh faham tak kat sini? Okay, so this example dekat gear tooth. So it's actually carburized, the ash. So kita tempered, so you can dapat area of gear hardened at the outside. Outside ni keras. So it's actually serve the purpose of the gear. Perlukan a very hard surface, but inner should be ductile so that it can actually work easily, because dia berpusing, bila pusing diperlukan ductility also, but the outer surface require hard surface. And this is micro hardness. Okay, micro hardness sama tadi as yang saya bagi tahu tadi. Ini adalah kalau kita kata hardenability, right? So hardenability dia sampai dekat 0.10. If let's say you have another sample that can reach more than that, you can see that the sample is more hardenability. So you can measure the hardness. So hardness akan drop when it actually reach a certain case of that. Okay, so the second method we call as nitriding. Berapa dia? The second method we call as nitriding. So as I mentioned before, you should have a former of aluminium ataupun chromium ataupun molybdenum or vanadium. So example adalah 4140, steel 4140. So steel 4140 have this alloying element. So when you have this alloying element, so you can actually combine with nitrogen tadi untuk form compound. So you can actually harden your punya surface. Remember that nitrogen will become solid solution, primary solid solution. So the first one is primary solid solution. So the second one will form secondary solid solution. So we need these two phenomena. Maksudnya kita perlukan solid solution dan kita perlukan juga formation of compound to increase the strength of the surface. So selalunya dia akan heated dulu dan tempered sebelum proses nitriding. So then they heated in the ammonia gas dalam at 500 to 600 temperature untuk lebih kurang 1 to 100 hours. It's very long period. So okay, you can also use different gas. This is gases of dia punya example. You can also use liquid. So gases sama ada gas nitriding ataupun liquid nitriding. So dia guna molten cyanide bars. So sama macam tadi dia ada guna solid kan, tapi untuk nitriding we only have two source, either gas or liquid. So for nitriding, so we don't have to use quenching because we don't want to form the martensite. So you have to ensure that you have to have former that can combine with nitrogen to form secondary solid solution. So the first, when the nitrogen is actually diffused, so it will actually go to the interstitial. Sebab nitrogen pun kecil. So another when the nitrogen reach a certain amount, so dia akan form compound dengan former dia, sama ada aluminium, chromium tadi. So they can actually increase the strength of the outer surface. So as compared to carburizing, nitriding lagi harder as compared to carburizing. So ini adalah proses dia. So this is ammonia. So nitrogen is actually will be diffused inside here. So leaving gases of hydrogen. So you get 2N plus 2H2. Okay, this is actually same juga. Dia kata require steel with alloy that form carbide with nitrogen. So you can tengok tadi depth of case dia dalam 0.8. Dia guna temperature yang very low. You can see that the hours is actually very long, 40 to 100 hours. Okay, the second method is cyaniding. So dia combine, dia ambil apa? Cyaniding apa? Nitrogen dengan carbon. So you must preheat a sample first. You kena preheat and you soak dalam. Okay. Sekejap ya. Lupa dah. Kita preheat dan kita dip dalam bus yang contain cyanide kan, untuk masa yang tertentu, dan kita perlu quench sebab kita ada carbon. Then we quench it, right? Then we will produce a thin hard shell which is harder daripada carburizing. Then temperature is actually lebih rendah berbanding dengan carburizing. So this is some of the microstructure illustrating the nitride cases produced by single stage process. So lepas tu kita tengok nitride dalam 48 hours. Okay, nombor berapa? Nombor 3. We also can do chromizing. Chromizing is actually to increase the punya to get the hardened surface for wear process also. And definitely kalau chromium kita ingat balik, kalau kita chromium kita akan bentuk chromium oxide which is good for the corrosion kan. Tapi dia require masa yang lama, and also dia punya durations also become very long. So you can actually use the same concept. Kita sama ada kita pack dengan chromium ataupun kita dip dalam molten salt. So normally what they will do, they will actually put a powder of chromium tadi, and then dia akan spray dalam machine, dalam macam some sort like macam kita buat apa nama dia, macam blasting tu lah, tapi dia akan powder tadi dia akan letak dalam satu compact. So dia akan masuk, kalau blasting kita spray ini dia akan masuk dalam satu macam kembung. Kalau granule tadi lah, kalau kita guna granule, or we can use dipping concept. We use a liquid because containing chromium. We use salt lah, kita soaking dia dalam liquid. Nombor berapa ya? You can also use boron. So dia normally untuk plain carbon. Plain carbon, as you can recall back, plain carbon tu you have less amount of element. Sebab tu kita panggil dia plain carbon. Dia ada element tapi very very less. So you can also use for tool steel. Tool steel has higher element, make it become hard. nickel and cobalt based alloy, and also for cast iron. So sama juga dia guna bentuk powder, salts and either gases. Dia kata casing with high abrasion and low friction dapat produce a very high surface hardness, then you can actually very high abraded, susah nak abrade, dan menyebabkan berlakunya kurang wear. So dia boleh reach around 70 HRC as same as nitriding. This is carbonitriding, so we combine carbon and nitrogen. It's also suitable for low carbon, and this is actually we preheat at the atmosphere containing hydrocarbon yang contain methane and propane, dan juga mix up with the ammonia gas. So dalam dia punya temperature around 760 to 850. By comparison, kalau kita guna carburizing is 900 and nitriding is 600. So nitriding is less, but it's prolonged. The time is very long, around 40 hours and 100 hours. It depends on the dia punya material yang kita guna. Sama ada former dia, ada aluminium, ada chromium and so on. You have to have a carbide former. It's not carbide former, it's not carbide former, nitride former, sorry. So we have to quench, selalunya kita guna gases, and also we can also quench dalam oil. So this is to ensure that less distortions of the part. So dia kata not suitable for high precision part because distortion are inherent. Definitely they will still have distortion, and if you have a part that are very sensitive, you can actually you cannot use this concept. Okay. Oh sorry, definitely you kena follow by tempering lah, sebab you ada dia akan dapat martensite, so you kena follow by tempering. Only nitriding, chromizing, boronizing are not required for quenching. But those yang ada carbon, definitely you have to go for quenching and tempering because you need to get a microstructure of martensite, and then you have to follow by tempering to get a structure that can actually sustain with high hardness but a little bit ductile. Okay. So this is actually second method, which is using heat treatment. So as mentioned before, so normally dia akan guna untuk medium or high carbon. Sebab carbon tu mesti banyak. Kalau carbon lesser, it unable to form martensite. So what they mentioned here, it must hit at the austenite region. Mesti patah balik, you call balik what you have learned, you must hit at the austenite region. Then after that, you quench it. Right? When you quench it, you follow the hardening process. Bila you quench, you akan dapat martensite. And after that, you temper balik. Sama saja konsep dia. Cuma the term saja berbeza. Okay? So you can have using induction heating, ini adalah depth of current, penetration, decrease of frequency, increase. You can guna induction, you guna flame, right? Flame spraying. So hardness is actually around 50 to 60, sama ada martensite or tempered martensite. So inner dia akan jadi lebih ductile. So you can see from this diagram. I won't go. Okay, you can see from this diagram. So you heat at the austenite region. So when you do a process of quenching, so you will get a martensite at the outer surface. Kan? Tapi dekat inner tadi, you akan dapat ferrite and pearlite. So you have a tougher core. And the outer will become harder. Same as surface hardening, right? Sama konsep macam surface hardening. Tapi ini kalau still dia adalah medium ataupun high carbon. Kalau sample tadi low carbon, kalau you nak buat martensite, you buat carbonizing. Tapi kalau you nak buat nak guna nitriding punya konsep, you boleh pergi buat nitriding. Tapi tapi still low carbon. Low carbon, then you can actually follow by nitriding. Kalau you ada medium carbon, kenapa you nak pergi buat nitriding, right? Better you buat heat treatment terus untuk turn dia jadi martensite. So you have to see lah what are the sample that you have. You cannot, if let's say you ada, contohnya you ada medium carbon, kenapa you nak masukkan, nak buat nitriding? Sebab you can go for martensite ataupun tempered martensite because you have enough carbon to form martensite. But if you have low carbon, you boleh pilih lah sama ada you nak buat carburizing, you nak tambah carbon, ataupun you nak buat nitriding, ataupun you nak buat chromizing, ataupun boronizing, cyaniding, and carbonitriding. It depends on the requirement. Kalau you nak increase dia punya corrosion, you boleh pergi kepada chromizing and as well as wear resistant. So it depends on the process, but you have to see what type of material you have. You tak boleh lah nak gunakan kalau you ada high carbon saya nak buat lah nitriding. You can do nitriding, but it's a waste, kan? You boleh pergi terus kepada hardening by quenching. You boleh guna terus this concept, you terus heat dia kepada region of austenite, so kat luar ni akan change to martensite. Boleh faham tak? Okay, so this is some of the example lah. Example tadi, this is induction heating. Dia akan guna electromagnetic induced energy. So dia akan heat the sample. Very fast heating, right? So you can guna untuk shaft. So tak ada gambar. Nanti dah saya akan letak video kalau baru you all faham. I'll try to find the video that you can see. So it's very fast heating. It will heat the sample up to the temperature of austenite. So for the shaft, you need a hard surface, right? Hard surface outer. So your sample might be medium carbon. So but you need a hard surface at the outer, so you will turn the outer surface to martensite and then you temper it. So this is a concept of induction heating. I won't actually go details on this. You can read. It's very straightforward. So you can also use flame hardening. So you can use combustion of the gas, which acetylene and propylene. So you can apply this torch at the outer surface, right? So dia kata tadi, kalau large part, selective heating part, so this is some of the reason. So bila you apply this heat, so what happen, they must ensure that the heat is actually up to the region of austenite. So pastikan bahawa dia melebihi dalam 900. Suhu dia mesti mencapai 900 supaya all the phases tadi dissolve become one single phase, which is austenite. Then after that you quench dalam water ataupun oil to get the martensite structure at the outer. Then you measure guna hardness tadi reading. So you can boleh tengok lah you punya hardenability tadi, depth of case tu yang tadi besar ke kecil. So you have to try and error. Sebenarnya bukan, tapi bila dah expert, dia know lah what are the temperature that require. But sometimes also you might have a problem in the production. Tapi selalunya dekat production dia akan mudahnya guna induction heating. Very fun. They won't go for flame. But I just show you this is some of the method. But normally people will not use this method unless a small workshop. Okay, so this is ni ni flame tadi lah. Okay, so this is high frequency. So dia akan ada selected. Maksudnya dia akan ada specific area of heat dekat sini. Okay? Bila you heat kat sini, so you can have a selected targeted area of heat that was supplied here. Then when the part is removed, so this will be quenched to the air. Kan? So you akan dapat harden kat sini, surface harden at this area. So this is another method we call as high frequency resistant. And you can use electron beam heating and also laser heating. But for laser heating, you doesn't have to be vacuum. So this is actually the dia punya advantage. Kalau you guna electron beam, so you have to vacuum it. So be another expensive. So dia perform dalam vacuum. So if let's say you use laser beam, so it doesn't have to go for vacuum. Okay, so but the concept is actually sama. You heat dia guna source of laser, yang satu lagi you heat dia guna source of electron beam. So this is some of example the hardness that you can actually get from the different surface hardening. So nitriding still will have higher hardness as compared to carburizing. So this is actually using induction harden. So this is you must have medium carbon or high carbon. So this is actually tough Through harden maksudnya normal concept, you guna furnace yang maksudnya semua bulk harden. So this you can see the different. If you need hardness more than 60, you have to go for knife grinding. This is some of the example furnace. I won't go detail on this. It's just a furnace type, batch or continuous furnace. Alright, so it's ngam-ngam 1 hour. Okay, so this is actually our last class for 2020. Wow, so fast. I think like 1 month, macam 1 bulan je berlalu. Actually dah 1 year, right? COVID dah datang ke Malaysia. 1 year, so fast, right? So so we will have another I'm thinking of doing another week of lecture on 4 until 8, but if I can't finish on 8, I will actually continue on 11. But I will do the test on 14th of January. So tolong tulis dekat calendar 14th of January. Tak masuk lagi Masuk tak lagi? Belum 48, siapa tak datang? Ada satu yang missing. Kita nak cari satu yang hilang. Alah, ada saya nak likan nampak ni. Sila kena bawa ni ke, bawa apa, bulu, apa nama, feather duster. Hish ada, Musih ada, Faiz ada,